divider bias. So what is bias? In electronics, in electricity, electronics, what is bias? Especially in electronics. This is something you need to know. So we've been talking about this just about all semester long, bias. And so I ask you what a bias is, and nobody can answer that question. So bias is a DC voltage we apply to semiconductors to establish how they operate. We have two basic biases. We have forward bias and we have reverse bias. The biases that we use in bipolar junction transistors or transistors, we have two types of transistors. We have FET and then we have bipolar junction transistors, which are still very, very popular according to the amount of power they can handle. So FETs have a lot of advantages as far as they consume less current, they consume less power to operate. They can switch fast because they don't have this stored concept that bipolar transistors have. So the bipolar transistors, these are the guys that can handle the power. So base bias, these are basically, we've already looked at that. These are going to be our a lot of our saturated switches. Emitter bias, we've looked at that. This is these give us these constant current sources that we looked at when I hooked up all those LEDs. That's when we put our bias resistor in the emitter circuit. Collector bias is not used that much, and voltage divider bias. This is predominantly the bias that we use when we want to amplify AC signals.
So bias is applying the DC voltage
to the base. Primarily to the base. It might, but that's what's using to set the parameters of the bipolar transistor. Is the bias connected to the base? Does that make sense?
What would the
base bias would be when the primary control is connected to the base. That makes sense?
When you say primary control, what do you mean?
Well, first of all, transistors don't create power. All transistors do is control the power that's already there. So when we say a transistor gives us power gain, it's not that it's creating the power, it's taking the power from a power supply and managing it, right? You understand? And then the power supply is taking some form of energy and converting it into electricity. So we can't create energy. All we can do is change its voltage, right? So I can take the energy stored with water and run it through a turbine. The turbine can turn the generator, and the generator is the transducer that converts water. Yeah, water energy over to what? Over to electric energy.
When you say primary control, you're referring to the transistor?
Yeah, the transistor. So we got three power supplies. We got one that we refer to as VCC. This is the primary source connected to the collector. Then we have VDD, which means the primary source would be connected to the base. And we have VEE. This would be the primary control is connected to the emitter. It might be that, and what we started off with is when we started looking at the transistors, we started off with two battery bias. So this is what you'll use when you the first one you set up. Oh, and then we come over here and then we put another battery up. Of course, this is not very good because now we have to have two power. So when you do this lab, and Lee's already done it, you couldn't use the trainer's batteries because the trainer's, power DC sources, they're connected like this. So it means I can't set this circuit up. So what did you have to do, Lee? You had to get another power supply. So we can use one power supply off the trainer, but we can't use both of them because they're not connected correctly. So this guy right here actually requires two power sources. And what we're trying to do is we're trying to get to where we can actually do it with one, right? But what it does, it allows us to come over here and change this on the base. So if I came over here and was moving this up and down, simulating AC, then my output over here would be moving up and down. So this is where we're moving toward, taking these things instead of using them as switches, which are used a lot. I mean, a lot. If you think about all the memory, all the random access memory inside this machine right here, every storage cell is a transistor. But it's used as a switch. The switch is either what? On or off. So switches are easy to design, but when we start putting AC into this thing, we're going to have to start taking compensation. And I gotta use AC, right? You understand? Because one thing, we live in an analog world, and first I would never have audio, because audio is AC. I actually showed y'all that the other day, right? When I talked to that speaker, it's what? It's AC. So if I want to listen to stereo, if I want to listen to the news, if I want to do any of these stuff, I've got to be able to do what? Amplify AC. Switches won't do that. So if I came over here with our switches, and we showed y'all that the other day, so this is a typical switch where we put our load up here, right? So here the primary source is on the collector. So this would be what we call collector bias. I bring my signal in here. So if I try to put AC on this, then what happens is it goes, while it's going positive, this would put a positive right there, and the transistor would cut on. But when it does what? It goes negative, the transistor wouldn't do anything. In fact, we could actually damage it because of the reverse breakover voltage, right? So what we would get out of here, every time it went positive, we'd get a pulse like this, and then every time it went negative, it would cut it off. So I'm not passing AC, right? So these switches, I mean, there's a lot more switches than there are AC amplifiers, right? You understand that? Because like I said, this guy here I think got 8 gigabytes worth of memory in it. Gigabytes. A byte is 8 bits. Each bit would be a transistor, right? You understand that? And that's not including the control circuit that actually controls the memory itself. That's just the storage element. So how many transistors will that be? That's a lot of transistors. A switch is just in what? Just in my computer. So by far, the switch is more, a heck of a lot more predominant in a digital world that we're in now. It's a heck of a lot more prominent than AC amplifiers. So even if I've got a DVD now, it's digital. Sooner or later, we're going to take that digital information and get it over to analog to run our speakers, right? You understand that? So in AC, so we'll look at that. The major problem with a bipolar junction transistor is that transistor beta changes with temperature. Now, we compensate for this with the switch by using minimum beta. So if we use minimum beta and the switch is saturated, you can't saturate it more than saturate. That'd be like trying to make a switch more closed than it's what? Than closed. So if the beta can't go up because the switch is saturated, right? You understand what I'm saying? If in a BJT used as a rheostat, this is the active region. This can cause major problems because temperature can, Chris. I just made this correction, so it's not. Because the temperature can also control the IC. And that would give us all kind of problems, right? Understand? So this is what we're going to have to figure out. So this is base bias. This is the one that we use. So here, of course, we're still connected to the collector, but the primary bias is over here on the what? On the base. That makes sense?
Primary power coming in on the base.
No, the primary control is on the base. Okay? So this is what we're trying to get into only one power supply, right? And then we use resistors to set the bias. So the resistors are used in this situation to determine what type of bias we have. So this would be, so the primary control of this, where it sets the operating condition, is the size of this resistor right here. That determines the base current. And then the base current would control the collector current, and the collector current would determine what our output is. That make sense? Yes or no? So this is a PNP transistor. This is an NPN transistor. This is a PNP. So a PNP, so notice here we're using a what? We're using a negative power supply. Because it's what? It's a PNP. The collector has to be reverse biased. That's very important to know. So since it's P, we're going to put an N, we're going to put a negative voltage on it. The emitter, we're putting a negative, so PN, this is negative, and then since this is common, then the emitter would be positive in respect to the base. Here we're forward biasing a PNP transistor with a positive power supply. So here we're putting a positive on the emitter. Then the base would be 7/10 less positive, and then this runs to common. So the collector is connected to common, so it's going to see a negative in respect to the base, right? Y'all see that? So we can forward bias a PNP with a positive power supply. But it's still base bias. Even though we're using DEE, it's still base bias because the base is controlling where the transistors operate. You understand that? So this is collector bias. So here what we're doing is we're controlling the base through the collector voltage. Now this is not used often because if you put AC on this, and right now we can't put AC on these guys because we know, so what would happen if I put an AC source right here? Yeah, so it would actually only give us half the waveform out, right?
So the indication of the base before it gets to that resistor is going off the pad down directly down to the base to identify that it's base 5.
Yes.
And the next 5 it switches after the resistor, so that kind of indicates to us that is collector bias.
Yeah, because one thing, this is the primary control of what's going on. That's right there. So that's controlling the base. So what's controlling the base current? Right? Because the base current determines. So this guy right here, so, if I set a 1K and this was a 1K, and then of course this drops 7.7 volts, then, if this is 10 volts, then this would be, I'd have to think about it, 4 point something, and this right here would be 4 point something. But this guy right here is setting the primary voltage that's going to be applied right there, right? Now the problem with this is that we can set this thing up to operate at a certain spot, but if I try to put AC, and we're going to figure out how we can put AC in a minute, I cannot bring AC directly into the base. Because one thing, it will cut off half of it, right? You understand that? So somehow, we're going to have to come up with a way where we can bring AC into the base and not have it cut off on the other alternator. No. We'll show you in a minute. So this is emitter bias. Now, what's nice about emitter bias is basically, we know if we put a resistor in the emitter, then we end up with basically what we call a constant current source, right? Y'all understand that? Yes or no? So if I come back over here, and we did this the other day, where I came in like this, and I put a resistor right there, and I made it 1, but no, I'm going to bring this straight in. I put plus 5 volts right there, and let's say it's 1K on, what would I have, we're forward bias, so what would I have right here on that resistor? 4.3. What would the current be? One milliamp per volt. What I like about a K is 1 milliamp per volt. So it'd be 4.3 milliamp. Okay, so what if I don't put a load right there? And I put 10 volts right there. Well, this guy right here is going to drop. It's not going to burn up because I've got a resistor in there, right? Well, this guy right here is going to drop 5.7 volts at 4.3 milliamps. Well, what if I come up here and put a resistor right there? Let's say I come up here and put a 1K resistor right there. Well, this guy's going to drop 4.3 volts at 4.3 milliamps. Right? You understand that? So this is what we was doing the other day. Is I came over here and I put a 330 ohm resistor down here. I remember this, 330 ohms. Okay, 330 ohms. I put 5 volts there, so that'd be 4.7 volts here. 4.3 volts there. So what would the current be? IC would be equal to approximately what? What's that? That's 13 milliamps. So I could come up here and I could do it like this. It's no problem, but it wouldn't be anything. But I came up here and put a diode right there. What's the current flow through the diode? And I put this up here. I think I put 12 volts up here. I was using the power supplies on something. Don't make any difference. What would the current flow through the diode be? 4.3 milliamps. I'm setting the current down here. I'm not setting the current by the diode. I'm setting the current by the what? By this resistor right here. Well, what if temperature went up? Well, beta can't change because I'm set. If this voltage right here don't change, then IC is not going to change. Beta is not going to go anywhere. It's wherever I set it to be. Right? You understand that? Well, what would so this could be germanium. It would do 4.3 milliamps and it would drop, for one thing, LEDs are not made out of germanium. And they're not made out of silicone because they don't produce enough photons. LEDs are made out of gallium, and then they're doped depending on what type of color you want. So if we don't know the drop, if we don't look up the LED, or if I don't buy it, we assume it's approximately 2 volts. Period. But it don't make any difference because with that resistor right here, I set my current at 13 milliamps. I don't care if it's red, I don't care if it's green, I don't care if it's blue. Well, what would happen if I come up and put another LED right there?
Oh, now notice the arrow down.
Oh, I'm sorry, I didn't.
Yeah, I was like, what is that?
I didn't put the symbol. So those are LEDs. What would happen? 13 point, until I run out of volts, right? So what happens, we were dropping about 2 volts. So and this guy right here is dropping 4.3. So when I got up to about 4 LEDs, I put another one in there and it didn't work anymore because I didn't have any more voltage up there. So technically I could put 50 volts up there and I could keep stacking those LEDs up there and it doesn't make any difference until they drop more voltage than supplied. So what's nice about emitter bias is this guy basically is not susceptible to temperature change. It'll run just like that, no matter what, if I don't change the voltage on the base. If I change the voltage on the base, then of course the current will change, right? You understand? So what will happen is if the base voltage right now is fixed at 5 volts. But now I could come in here and I could do this. So it went up, my base voltage would go up, my current would go up when it went down. So now I've got 5 volts there that I can add to and subtract from it, but I can't bring it into the base directly. Can anybody know why? First of all, I have to set it at 5 volts, and I'm burying it, but we'll look at that in a minute. So this is voltage divider. This is the most widely used bias, and I'm not recording any of this stuff. This is the most widely used bias in AC circuits. Can you see why it's called voltage divider bias? Yeah, all we got is a voltage. So the base voltage is set by this voltage divider right here. And then we'll look at this what's going on over here. So what's the purpose of this resistor right here? This is going to let us ignore beta. So whatever I set that current at, it's going to be no matter if it's 100 degrees or whether it's 30 degrees outside, it's going to be there. So that resistor there is for temperature stability. So this is the equivalent circuit. How many of y'all can solve this circuit right here? Where did you learn how to do this at? DC. Of course, you can't solve it now because I had given you any values, right? So this is the equivalent circuit for voltage divider bias. So basically, this is the transistor right here, and what I'm doing is I'm controlling the transistor with this voltage right here. So what would the voltage across R2 be? Get out your calculator. R2 is setting the bias on the base. How would it be 30 volts? It's a voltage divider. So you're saying R2 is dropping 30 volts. Well, you just ignored R1. The sums of the voltage drop in a series loop. So what we're doing is we're ignoring the transistor, and I'm solving for this circuit right here, and I want you to solve for R2. VR2. So anybody got that? Huh? So it's still here, instead of using Ohm's law, I would use that voltage divider formula, where VR2 would be equal to R2 over R1 plus R2 or RT, right? And then I would come over here. And a lot of this you can do in your head. How many of you can add 22 and 10 in your head? And then I would multiply this by 30. So VR2 would be equal to 10K over 32K. K is going to cancel because it's on the top and the bottom. So 10 divided by 32. And then when I'm going to come over here and I'm going to multiply that times 30, and then that's going to give me my vote. So in a series circuit, we don't need to calculate current to calculate voltage drop. This is really big. So what do we come up again? What's that? Why? So I'd say 10. Why can I drop the K?
And it's both the same.
It's the same, right? If anytime on division, if the top and the bottom are the same, you can drop it. And then I can come up here and I can divide that by 32. Equals that. I don't have to worry about engineer notation because I'm not going to give that answer. And then I'm going to multiply that times 30. So Cameron said 5.4 votes.
I can find what this is on the same thing. I just have to get the current.
Yeah, you can use 10K and 32K if you want to. But what I learned and a lot of times when you learn this little trick, you know, that a lot of times you can almost get the answer without thinking about it, right? So 9.4 votes. Everybody okay there? 9.4. So what would be our one? According to Kirchhoff's law, the sums of the votes you drop have to equal to the applied voltage. So I'd say 30 minus 9.4. That. I missed what did it say?
20.6.
What was VRE equal to? So I'm putting 9.4 votes right there. So what would VRE be equal to? Is it forward bias? So I've got the emitter connected toward common. I've got a plus 9.4 votes on the base. This is an NTN, so is it forward bias? Yes or no? Is the emitter more negative than the base? Yes or no? So is 9.4 votes more positive than circuit common? We consider circuit common to be 0 votes, right? You understand that? So sure, it's forward bias. So what would VRE be equal to? Well, we're going to treat this guy like one of these right here. So how much voltage is the base to emitter going to drop? If it's silicon, it's going to drop about 0.7 of a volt. So what would VRE be equal to? Well, VRE is going to be equal to 9.4 minus 0.7. So what's that going to be equal to? Oh, I needed to put another calculation in here. I'm short one calculation. I'll put it in there later. So what's VRE equal to? So VRE is equal to 8.7 volts. So I know the voltage drop across RE. I know the size of RE. So what can I calculate? Current. So I can calculate current. So I can calculate IE, but we're assuming IE and IC are equal to each other because they're almost equal to each other, right? So that's the one I left off. So IC would be equal to 8.7 divided by 1K, which would give us 8.7 milliamps. Well, I know over here this is a series circuit. I know this got 8.7 milliamps flow through here. Of course, we're going to lose base current, but it's going to be back in the microamps, so we're going to ignore that. And we're going to say that IE is equal to IC. So I don't know the resistance of the transistor. It's acting like a rheostat. But I do know that RC is equal to 1K, and I know it's got 8.3, 8.7 milliamps flowing through it. So what's VRC going to be equal to? It's going to be 8.7 volts, right? Everybody understand that? So I'm going to show you the math. I don't mind. So VRC is going to be equal to IC, which is a series circuit. So once I calculated it here, I know it's there, right? Now, if you see on the test it says IE and IC are equal to each other, that's going to be false. IC is approximately equal to IE. The only difference between IC and IE and IC is the base current. The base current is going to be down in microamps. So for all practical purposes, for calculations, we're going to assume that IE and IC are equal. Why? It's not enough, and we're dealing with all these, we're calling that a 1K. What's the odds of that being a 1K? Right? We're calling we're calling that a 22K. We're calling that a 10K. We calculated exactly 9.4 volts. What's the odds of me measuring 9.4 volts? But it's going to be what? It's going to be close. Where I can tell if it's what? Good or bad. And this is what bothered me about on some of your power supply lamps. You come over here and you calculate 12 volts, and over here you say you measure 6, and you just keep going on. When you should realize that what? That something is wrong, right? Either you did what? Either you did your math wrong, or the device is bad. So we got a power supply back there. We'll look at on one of our trainers. It's gone bad. Well, it's not going to do me any good if I don't know what I'm supposed to measure before I put my meter in it, right? And we'll see how easy these power supplies are to troubleshoot. This guy right here is fairly easy to troubleshoot too, if you understand these bias codes.
What's the guy do about
Okay, VRC is going to be equal to, V is equal to I times R. So we're going to say 8.7 milliamps times 1K. Equals 8.7 volts. Now, the only reason that we should have known that because we got 8.7 volts here. It's a series circuit. This is 1K. That right there is 1K. It's a series circuit. So if it's a series circuit and current is the same, resistors of the same size will drop exactly the same voltage, right? Okay, VC. VRC is nice to know, but that doesn't tell me where the transistor's operating in. It does not tell me if it doesn't tell me if it's in the active region. It doesn't tell me if it's saturated, or it doesn't tell me if it's cut off. So my output, this is where we're going to take our output right here, eventually. So this is going to be V out, once we figure out how to do that, and this right here is going to be V in. So V out is going to be taken across this circuit right there. So VRC is okay, but my output is not going to be 8.7 volts. My output is going to be what's left over. So according to Kirchhoff's law, the sums of the voltage drops have to equal to the applied voltage. All right. I know that that RC is dropping 8.7 volts. So I'm trying to figure out what's left over between that point right there and common of the circuit. So VC is going to be equal to VCC minus VRC. That's what's going to be left over, right? You understand that? What's that? So, voltage collector to emitter. We're going to take the voltage on the collector, 21.3. We're going to subtract from that the voltage on the emitter. What's on the emitter? 8.7 volts. Voltage collector to emitter. We're going to take what's on the collector, collector to base, 21.3 minus what's on the base, 9.4. So those basically give you the formula. So is this guy operating in saturation? Is it operating in cutoff? Or is it operating in the active region? Why? Yeah, less than 1, you're right. So this is operating in what we call the active region. Now, if I could bring these, an AC signal, somehow, if I could bring the AC signal in, now this is not a good amplifier. This guy right here would only have a gain of 1, by the way. We'll figure out how we calculate that. A voltage gain of 1, which means it's a waste of time, but it's good to learn how to calculate these things, right? Now, why couldn't I bring an AC signal directly into the base? We demonstrated that in class the other day. Well, no, because we got 9 point. It looks like if I bring the 1 volt peak to peak in here, it looks like when it goes positive, it would go to 9.4, and if it went to negative, it would subtract, right? So now that we got the base sitting at a voltage, it looks like I can add and subtract from that. But the problem is I can't. So this is what we looked at the other day, is I came over here, up here on my trainer, I have a 1K, and I had a 1K. And then I've got this connected to the 5 volt supply. And of course, when we measure across this resistor right here, we would measure 2.5 volts. And then what I did is I came over here and I put an AC signal in right here. Very small AC signal. Right now, when I measure with my meter, here's first common, turn it on. Let me raise this up so I can put my meter. Okay, so here's my 1K, here's my 1K. I'm going to come over here, and I'm going to bring an AC signal. So here's my AC signal right here. Here's my AC generator. And what I'm going to do is I'm going to measure right here at the center of my resistor. Measure about 6.5 volts. So I'm going to measure right in the center. I'm going to measure 6.5 volts. 6.5 volts. Okay, so here's my AC signal right here. And I'm going to bring it in between my two resistors. What's the measure now? So I'm going to take my AC signal away. Go goes up to 2.50. I bring my AC signal in and it goes down. It usually goes down to 0. I don't know what's going on. So what I'm going to do now is this is my DC common right here. What I'm going to do now is I'm going to come up here and replace this with my AC signal. So I'm using my AC signal as my common. Now I come up here and measure 2.50. So a DC source sees an AC source as a straight piece of wire. An AC source sees a DC source as a straight piece of wire. So you just notice that. So if I tried to bring my AC into that center of that resistor, then my top resistor started dropping all the voltage because it was seeing the AC signal as going straight to common. You understand that? So what that means is if I came over here and brought my AC signal, if I come in here and brought my AC signal, if I tried, even though I'm sitting right here at 9.4 volts, if I was to come over here and do this right here would drop to 0. And 22K would drop all the volts. So an AC signal, a DC source sees an AC source as a straight piece of wire, and vice versa. So I just demonstrated that. So I cannot bring an AC signal directly into the base. I need something that will let the AC signal come in and block DC. So what device have we talked about all semester that passes AC and blocks DC? A capacitor. So all I have to do is, and I have to use the right size, guys, all I have to do to bring an AC signal in is I can bring an AC signal in through this. And we have to, it's going to be polarized, so we have to put the plus on that side because the capacitor sees that other thing. It's right. So now I can bring an AC signal in. So what I can do, I wish I had my scope still hooked up. I think I do. So here I'm going to put my common back over here. And here I have a 10 microfarad capacitor. Let me switch back over to my camera. Well, it is. That's what it's going to do. It's what it's doing. It's going to superimpose the DC signal on top of that AC. Okay, so here's my capacitor. I'm going to put the negative port of the capacitor. I'm going to put it into between the two. And I'm going to bring my AC signal in here. And then I'm going to measure the bias. I don't have enough bias. See, so now it's still got me see. So even though I'm bringing that AC signal in, my voltage is still set to what? 2.5 volts. So now it's not seeing it as a source. But when I come up here and look at the actual signal itself, it's riding on DC. So there's the AC signal there. Here's 0 volts. Here's 0 volts. And what it's doing is adding and subtracting to that bias voltage. So putting that capacitor in there allows me to bring an AC signal into the DC bias, and it's going to change the base voltage. So that means when this voltage goes up, it's going to turn the transistor on board. When the voltage goes down, it's going to turn the transistor, it's going to move it toward cutoff. So here's 0 volts. There's 2.5 volts. And what's it doing? It's adding to it or subtracting from it. But when I look at it with my meter, my meter is going to show, it's going to ignore that AC. So it's measuring 2.5 volts. Why? Because the DC equivalent of a sine wave is 0, right? You understand that? So what it's doing, your meter is measuring right down the center of it, which is 2.5 volts. So that means if we can measure the bias when there's AC on the circuit. So your amplifiers, you're going in there and you're checking the bias on the transistor, and you got it turned up wide open, and you're not saturating the transistors, the bias will still be right, because your meter's going to do what? Your meter's going to go right down the center of that AC signal. But you got to put your meter on DC. Then it ignores the what? It ignores the AC. So what's the DC average of an AC sine wave? 0. So where's your meter going to do? Your meter's going to go right down the center right here, which is 2.5 volts. But now I have the ability to add to the base bias, and subtract from it, which is pretty good. So now using that transistor, now this is going to set the low end response of that, because this guy right here, we're not going to look at that. So we're not going to calculate. We could actually calculate the bandwidth of this amplifier. The range of frequency this guy shoots at. So X of C is equal to 1 over 2 pi LC. So you know if I put a DC signal in this thing, it's not going to get through. 1 hertz is going to let it vary through, 3 hertz. So every audio amplifier has what we call a bandwidth. And what's the bandwidth? We talked about that the other day, right? The range of frequency is passed. And what happens if the frequency gets too high, it starts jumping across these junctions, and we lose control of it too. So the transistor sets the upper limit, and then your capacitors, your input, or your coupling capacitor sets your lower band. But it's no big deal for us because we don't have a real wide frequency response, right? You understand that? Our upper limit is around 15 kilohertz. Some people can hear higher than that. Some people, depends on where you're at or what you've been exposed to in your life and what's going on with your ears. When we get down to below 30 hertz, we just hear what? We just kind of hear clicking. So now the problem is, if I come over here now and I put, so this thing is sitting here. This is sitting at 8.7 volts. If the temperature tries to go up, if the temperature goes up, it's beta going to change. It can't because we've got IC set. We've got IC set at what? We've got IC set at 8.7 milliamps. If temperature tries to go up, it's not going to change because we have the emitter current set. Right? You understand? But when I come over here and add a signal coming in, so let's say we put 1 volt, let's say we put 2 volts peak to peak. This right here is sitting at 9.4 volts. Now, so temperature can't change the emitter voltage, but an input signal can. So if I come up here and put 1 volt peak to peak, then what's going to happen is 1 volt, this is going to go up to what? 10.4. It's going to cause the voltage across the emitter to go up to what? 9.7 causes our current to go up to 9.7 milliamps, causes this guy right here to drop 9.7 volts, causes this output to start going down.
I remember we used beta to get it turned. What was that one?
We're not using beta right now, and that's what's nice about this. That's what's nice about a common emitter amplifier. We can set the beta of, as long as we keep this thing between, if it's a 2N3904, as long as we keep the beta between a 30 and 300, we can set the beta wherever we want it to.
Gotcha. Okay.
But we'll use a beta, and the problem is when we start looking at why do we, when we calculated this voltage drop right here, why did we ignore RE? Well, that's determined by beta, right? We'll look at that in a minute. Why can we ignore RE, even though we have a path for current flow to get to RE? Yeah, we're going to get to it.
How can you calculate RE to R1, R2, anything over RE?
Well, we know RE. We know that if it's a silicon transistor, we know the difference between VB and VE is going to be 7 volts. But we've got this, so the circuit we have is we got this over here, and then we got this, and then we got RE. Well, it looks like this guy and this guy are in parallel with each other. But when we calculated that 9.4 volts, we ignored RE, we ignored that 1K. And we'll look at why we can do that in a minute. And these are going to be very, very close. The problem I have now is that this is going to go, what did it go to? 9.7, we subtract 9.7. So VPC would be, VC would be equal to 30 minus 9.7. So when the input goes up, the output goes down. Y'all understand that? Because when the input goes up, it turns the transistor on more, which causes RC to drop more voltage. So what did this come up to giving? What's that?
20.3 volts.
So when the input went up 1 volt, the output went down, whatever that was.
Yeah, it was originally 21.3, now it's 20.
Yeah. What we're going to find out is, this is, like I said, this is good to calculate because of the size of the resistor. Normally your collector resistor would be a lot bigger than your emitter resistor, and we'll look at that in a minute too. But we're just using this circuit. It's a very poor amplifier because it's only got a gain of 1. So what would be the purpose of me having an amplifier that does not give me a gain more than 1, right? And we'll see how we can calculate the gain. Basically, the gain is this guy divided by that guy. So 1K divided by 1K, that's 1. But if RC was 2K and RE was 1K, then the thing would have a voltage gain of 2, which means I would get twice as many volts out. Now, we're not creating voltage. We're not creating current. Where does the voltage and the current coming through that we're controlling? VCC. And where did VCC get its power from? From Alabama Power. Where did Alabama Power get its power from? Spinning turbine, right? Where did the turbine's power come from? Well, we're going to take water and convert it over to what? The gases and use that, or we're going to use, so we can't create energy, we can change its form, right? You understand that? So a lot of people think that the transistor creates power. It does not create power, it controls power from a power supply. And that's why we call these things power supplies. We don't call them voltage supplies, we don't call them current supplies, we call them power supplies. And they got their power from something else, right? You understand? But what I'm saying is this output is going to be riding on top of DC also. So my output's going to be riding on top of DC, and my input's riding on top of DC. So if I want to get AC out, if I want to put AC in and get AC out, what am I going to have to put on my collector? What blocks DC and passes AC? A capacitor. So this is basically what the circuit ends up looking like. We call these coupling capacitors. The bigger they are, the better the lower bandwidth. And there's, I don't know if I gave you the formula to calculate what we call the cutoff frequency. We can calculate the cutoff frequency. We can calculate the input opposition. So let's look and see. Let's start back here and let's look and see why we can ignore RE when I calculate that voltage right there. Okay. So we have this sitting at what? 9.4. That gives us what? 8.7 right here. Then we got IC would be equal to 8.7 milliamps. But that's not what we're looking at. So we're going to assume a beta of 100. So 8.7 milliamps. How much base current would it take to get 8.7 milliamps to flow? So IB would be equal to IC divided by beta. So IB would be equal to 8.7 milli divided by 100. What would that give us? $87 micrograms. Okay, so our base is seeing over here, it's seeing 8.7 volts at this current right here. So R of what the base is seeing, it's seeing 8.7 divided by 87 microamps. So B over, it's what the base sees, right? So the base over there on the emitter, it sees 8.7 volts, but it don't see it at 8.7 milliamps. It's seeing it at 87 microamps. So what does the base see that RE as? It don't see it as 1K, it sees it as 100K. So the emitter resistor is seen as, from the base point of view, it's seen as times base. That's what, so this signal coming, this right here sees this resistor over here as a 100K. Because when it's at 9.4 volts, it only requires 87 microamps to cause that to drop. Okay, so what's 10K so technically the actual bottom circuit would be 10K in parallel with 100K. So what's 10K in parallel with 100K? What would that resistance be? You can use product over sum. You can use sum, reciprocal, sums over reciprocal. $99K or something. 99. So we call it the 10-to-1 rule of electronics. If you got two resistors in parallel, for approximation, if you got one that's 10 times bigger than the smallest one, you can ignore the bigger. But think about the math. So you use 99.99K, and then you divide that, you still come up to get 9.3 something volts. So what's the difference between 9.3 and 9.4? So for all practical purposes, we can ignore the emitter resistor because it's seen as times beta of the circuit, right? Understand that? So when we calculate that bias voltage, which makes it easy on us. So in a series circuit, if I've got a series circuit and I've got a series resistor that's 10 times more than a resistor that it's in series with, I ignore the smaller for approximation purposes, right? To understand, it's not going to be perfect, but when we get into transistors, guys, we're going to learn that there's so many different variables that none of our math will be perfect, but it will be close enough to determine if the circuit is good or if the circuit's bad. So when I calculate that 9.4 volts, I'm going to ignore that emitter resistor because it's seen as times beta. Now, if beta disappears, that's going to give us a problem. Because if beta disappears, it's going to be 1K, and that's going to be one of the things that we're going to look at. So what is beta? It's IC over IB. So if we lose IC, then your base is going to see that as a 1K. But as long as IC is there, it's going to see it as times beta. Okay, so let's calculate this. So what would VB be? That's all we're concerned with right now, because that sets everything up. It's going to drop 1/10 of the vote. I'm sorry, 1/11 of the vote. Or 10/11 of the vote. We can't drop that.
I got 1.8. That's what I calculated.
Everybody okay? Anybody want to see how Mario got that? Nobody saying anything. Huh?
How do you get 1.8?
Well, we got a couple ways we can do it. So I can say it's a series circuit. We're calculating the votes you drop. R2 sets the base vote. R2, right? You understand? So I would come over here and I would say 10K divided by 100K. K's cancel, right? You understand? Then these two zeros cancel. So it's going to drop about 1/11 of the vote. 1/10 would be 2 votes. You see that? You understand? And then I multiply this times, I multiply this times 20. What we can do, the voltage of a series circuit, a resistor drops a voltage relative to its size to the other resistors in the series circuit. So it don't make any difference. I could have 15 resistors in series, and I could calculate R1 by taking R1 divided by R2. So what we're doing, and then multiply it times the voltage. So I could come over here, I could change this to 30 volts, and it would still drop 1/11 of the voltage. I could change it to 15 volts, and it would still drop 1/11 of the voltage. I don't think they teach in DC, we're supposed to teach voltage dividers. And what's nice about the voltage divider formula is you don't have to calculate I. So what we're saying is I can come over here, I want the voltage drop across R2. So the voltage divider formula says VRX equals VRX over RT times the source voltage. Of course, here it's going to be VCC. So what do I want the voltage drop across? I want it across R2. So I'm going to say VR2 would be equal to 10K over what's RT? 110K, right? And that's what's nice about the voltage divider formula, especially on these. Most of the time, you can come up with RT without even picking up a calculator. And this is K also. Well, what's some things I know? Well, I know if it's on the top and the bottom, they can cancel out, right? So that marks out the K, that marks out that 0. So I know R2 is going to drop 1/11 of the voltage before I pick up a calculator. So 1/10 would be 2 volts, but 1/11 is going to be slightly less. Times 20.
Are we going to use 0.7 meter?
That was not there yet.
Can you remind me of the rule of thumb for the equivalent capacitor polarity?
Well, the problem is over here, this is an AC source. So from a DC point of view, this is seen as common. We just proved that. So that means this is plus 1.8, this is 0 volts DC, this is 1.8, this is 0, this is plus 1.8, this is 0. Which side is positive? What's more positive, 1.8 or 0? Okay, so that means I gotta put the plus toward there. Now over here, this is 0 over here, it's gonna be AC out, right? You understand? So a DC source sees an AC signal as 0. Now we might have to change this later on when we add another stage. So right now I have plus something right there. I don't know what it is. We hadn't got to it yet. And I got 0 on the other side. Now eventually what we're going to do is this does no good either. Because I've got an amplifier. It's got a gain of 10. But I'm not feeding it into a wall. I'm not getting any work out of it. So eventually we're going to have to do what? Eventually, guys, we're going to have to come up here and hook this up to some type of load. And it's going to be considered a resistive load even if it's another amplifier. So normally what we do when we amplify, we go through stages. So right now, the maximum voltage I could bring into this would be probably 1 volt peak P. Because I'm going to add, if I ever get down below 0.7 of a volt, transistor's going to cut off. And what we'll do is we'll clip the top. We'll just do some units. So we call that distortion, and I'll deliberately put it into distortion. So you understand? Does that make sense, Mario? Yes, sir? So right now, here's 0 volts down here. Here's plus some voltage. So that means we have to we'll put the plus toward the collector. So that's plus DC, right? Does that make sense? Over here, this is seen as 0 volts as a DC reference, right? So so I'm putting AC over here. What's the DC average of an AC sine wave? What's the DC average of an AC sine wave? 0. So that means this capacitor is not seeing this as AC, it's seeing it as 0. This is plus 1.8, right? So that's why the plus has to be pointed toward the baseline. Now over here, this is going to be a plus voltage that we haven't calculated yet, but I know it's going to be plus relative to whatever I connect this up to. So eventually we would connect it up to another amplifier. So this guy here only gives us, we could only put, so this AC voltage could go up 1 volt. So if it goes up 1 volt, we're going to get 2.8. If it goes down, no, we can't. If it goes up 500, so we've only got, yeah, we could go 1 volt down. So we could put a 1 volt peak to. So if it goes up, this will go up to 2.8. If it goes down, it's going to go around 8.8 volts, but that's getting close to cutoff, right? So what we're doing is, I have the circuit set up, by the way. So this is the oscilloscope. This is the base. Now I'm bringing this to the capacitor. So that's why it's giving me AC. This is before the capacitor. So coming in, so it's 1 volt coming in, 1 volt peak P coming in, and I'm getting what out? So channel 2 is sitting at, oops. No, this is channel 2 right here. This is channel 1. So yellow is channel 1. Blue is channel 2. So I've got it on 500 millivolts per division. So that's 1 volt peak P. And I have it on 2 volts per division. So on my output, I'm getting 2, 4, 6, 8, 8.5 volts. But one thing you notice, if I get my camera up closer, this is a characteristic of this amplifier, where when it goes up, the transistor cuts on, so the collector voltage goes down. When the input goes down, the transistor moves toward cutoff, so the output voltage goes up. So the characteristic of this amplifier is that your input and output are what we call 180 degrees out of phase. You see that? Here's my input. Here's my output. But it's an exact replica of the input. It's an exact replica of the input. It's just that it's got gain on it, right? And it's 180 degrees out of phase. Now in sound, it makes no difference as long as your left channel and your right channel goes through the same amount of phase shift. That makes sense, because your ears are not listening to phase. Your ears hear two things. It hears amplitude, right, and frequency. So this is the actual circuit. It's hooked up down here. So here's my input capacitor. Here's my output capacitor. And I'm hooking this up to a 100K resistor. So that's why I'm not getting a gain of 10, and we'll look at that too. But if I take my scope and put it on the base, so here's AC. I'm going to take my scope and put it on the base. So here's 0 volts. Oh, sorry. Here's 0 volts. Here's 0 volts. So that AC, you bring AC in. So here's 0 volts. You bring it to our coupling capacitor, and now it's riding on top of what? It's riding on top of DC. But with that capacitor, it allows us to bring an AC signal into a DC. Here's my collector. So where's my other channel? Here's my collector. So this is off my collector right here. So here's 0 volts. Here's the collector. So here's 0 volts. So it's riding on top of DC, right? But if I take it and go through that capacitor, here's my load. Now I see AC. So what that capacitor does, so the transistor is not an AC amplifier. The transistor is a DC amplifier. But using those capacitors, I can bring AC into it, couple it into DC, make the DC change at an AC rate, right? You understand? My collector, I get AC riding on DC. Then I bring it to a capacitor, and then I get AC out. We call those coupling capacitors because that's what it does. It couples AC in and does what? It couples AC out. So and the bigger they are, the more they cost in farad. But it lowers your lower frequency cost. And what's nice about coupling capacitors is they also isolate the stage, so you can blow out one stage in your amplifier and not have any effect on the stage before that. So normally when we go through stages of amplification. So we start off with an extremely small signal. So think about the voltage you're getting off the antenna of your car. And yet you're getting 30, 40 watts over on the other side, right? You understand? So we can't get that much gain out of one stage, right? You understand? So we usually go through multiple stages. And the output stage is going to use another range. But what we see that the only thing that goes on here is that your input and outputs are 180 degrees out of phase for this amplifier right here. So we said we had what? 1.8 volts right there. Everybody okay there? So what would that give us on our emitter? It's going to give us 1.1 volts on our emitter, right? Okay. So VE is going to be equal to 1.1 volts Or what's IC gonna be? We're calculating IE, but what was the difference a while ago between 8.7 milliamps and 87 microns? It wasn't even enough to do what? What's that? So I equals 1.1 milliamps. Oh crap. Chose the wrong array, guys.
No, if you could say, technically calculate, IC without having, DV.
What would you think?
I don't know, I had a question.
How many more would you think? Where does V, I can't calculate, so to calculate current, you gotta know two things. You gotta know V, and you gotta know R. What sets the voltage across RE? VB. So, and that's why I wanted you to do. I wanted you to answer your own question, right? Understand? Because where does that voltage come from? It comes from the base. So here we calculated 1.8 volts. So that's VG. Everybody okay there? Then DE would be equal to 1.1 volts. IC would be equal to 1.1 divided by 1K. 1.1 daily. Yeah, that's what I like about volts over K. It's all, you just take the voltage and throw it over. VRC, which would be next, VRC would be equal to 10K times 1.1 milliamps. 10K, guys, sorry. About 11 volts. 11 volts. Huh? Yes, no? What do we get for the vote? VRC? What did you say, Kim? I'm calculating the voltage drop. I'm calculating VRC. And it's a series circuit. So a series circuit, the voltage is the same. So as soon as we set this voltage right here, as soon as we calculate that current right there to be 1.1 milliamps, then now I know the current, since it's a series circuit, I know the current through this resistor right there. So now if I know the current through that resistor, I can calculate the voltage drop across it. Does that answer your question? So where did you learn all these formulas at? Except voltage divider formula, that's easy to use. But where did you learn all this at? DC. Well, you're supposed to learn, let me rephrase it. Where were you supposed to learn this at? Yeah, that's what, but where were you supposed to learn this at? But this is what's so neat. So you learn all this stuff back at DC, and all the resistors do in DC is drop a voltage and create heat. That's all they do. That's all they do. Here we get into solid state and we learn about bias. So what do we do to bias? We use resistors to set bias. So so now these resistors have a function in life besides doing what? Creating heat. We use these resistors to set the bias. So we use series resistors on Zener to keep them from burning up, to drop the difference between the unregulated voltage and the regulated voltage. We use resistors on LED so we can put 5 volts across them even though they drop 2 volts, right? You understand? So now you have a function of why we want to use these resistors. What's the function of resistors besides creating what? Creating heat, dropping the voltage and creating heat. So that's what you learn. But you learn how to calculate parallel circuits, series circuits. These are, you did probably a lot more complicated series parallel circuits than this guy. So one side we got two, so we're treating them like series resistors. The only thing that we got to know is what sets the voltage right there. Well, what sets the voltage right there is whatever I calculate across R2. Now, R2 is a general term, right? You understand that? This is nothing but the established formula. In true life, R1 might be R53. And R2 might be R10. And it won't be RC, it might be R4. It all depends. Normally, when they start numbering resistors, they start at the top left-hand corner of a circuit board, and they number them across. I'm saying normally, but it's actually up to the engineer how they do what, how they number the resistors. So I'll show y'all some actual circuits where we see R1 like this. So schematics shows you the logical operation of the circuit. It does not show you how the circuit is actually constructed on a circuit board, right? And we see that in this class where you try to do the circuit exactly the way it's drawn. So you try to measure, you try to measure VB and you try to get the base of the transistor when you can measure it what? You can measure it on this lead or you can measure it that lead, right? Which is a lot easier. So that's what I'm going to do when I measure these. So 1.8 volts. Now I've got the circuit set up here, so we need to figure out. So we got VRC. So what would VC equal to? VC, according to Kirchhoff's law, is the difference, right? So this is going to be 20 minus 11. So I should expect to measure about 9 volts on this circuit. So this guy's in the active read, right? So here's the circuit. Probably going to be sideways, guys. Now, let me turn it this way. And I recommend if you look at these circuits up, that you spread them out a little more than I did. But I'm going to show you how simple. So here's the circuit. So here's I'm using a 3904, which has a typical beta, by the way, of about 100. And we can calculate that too, but that's a little harder. Here is my brown, black, yellow. What is that? So here's R1, 10K. Here's a brown, black. Sorry, this is 100K. Oh yeah, this is 100K. Brown, black, yellow. This is brown, black, orange. That's my 10K. These two right here on the middle. This is connected to the base. Over here, of course, this is VCC. So I've got the 100K connected over here to the 10K. So here's the 10K. It's connected to, by the way, the emitter is on the left and the collector is on the right. Well, this is one of the ones that y'all figured out. So I've got a brown, black, orange, which is a 10K. I've got it connected to the collector. Here's my emitter resistor. That's my 1K right there. I'm going to take my meter. And it's active. It's got an AC signal coming into it that I showed y'all that. And normally what we do is we make our measurements to circuit common. And that way you're only probing with one lead. So that's why when we calculate these, we try to calculate them relative to circuit common. So here's my base. I'm going to hook it up to my input capacitor right here. here's my base. We're expecting what? It's got an AC signal on it, but my meter's going to ignore that AC signal. Here's my base. We calculate 1.8, it's measuring 1.7. Here's my emitter. We calculate, we're measuring 1.09. Like that. Here's my collector. 8.9, I think we calculated 9 volts. So it's not perfect, but it's what? Close. And by the way, guys, this is your main tool for troubleshooting these transistor amplifiers, is understanding this bias. If the bias is wrong, then it's going to identify what problem we have. So I can measure this bias, and I could almost guarantee that we can figure out where the problem is just by measuring the bias. So this is my input. I'm bringing it in, and I'm looking at the capacitor, by the way. So let me get it up so I can trigger it. So the input is applied across the emitter resistor. The output is taken across the transistor. So technically we can calculate the gain right now just taking the collector and divide it by the emitter. Okay. But mine's a little low, and we'll explain that in a minute. So mine's loaded. That is the unloaded gain. So the unloaded gain is RC divided by RE. Unloaded. So the blue is mine. So if it was unloaded, I should expect a gain of 10. But we're going to see it's going to be less because mine's actually loaded. So here's N. So N, I got 50 millivolts per division. So I got 150 millivolts N. Everybody okay? Y'all see how we did that 50 millivolts per division? I got 3 divisions. My bottom one, I've got it on 500 millivolts per division. So my bottom one, I'm getting, that would be 500 millivolts. That would be 1 volt, about 1.8 volts. So 1.8 divided by, that would be the voltage gain, out over N, right? 1.8 divided by, what am I putting in? 150 millivolts in, 1.8 volts in, out, so we get the gain of not exactly 10. They're 180 degrees out of phase, because when the input goes up, the transistor turns on more, causes it to drop more voltage, right? So the only disadvantage, and it's not really a disadvantage as far as audio is concerned, is your input and output on this amplifier with the 180 degrees up. Now, of course, if I start dropping the frequency way down, this 10 gives us a pretty good frequency response. You see how low that, so we've lost our gain. Up to that. Here's the input. But as the frequency goes up, the output starts going up. So this is what we call a bandwidth. Bandwidth is the range of frequencies this amplifier could have. And I don't know if I've got y'all our problem is not designing these things. There's a lot to design, especially when it comes to impedance matching. Impedance matching is really rough on these things. So that's one advantage that FET has over a bipolar transistor. You can match impedance really. So these things are not easy to design, but once they're designed, they're fairly easy to calculate to see what they're supposed to do. So that was really neat. So, of course, in real life, you know, your stereo, this is going to be all over the place. In fact, I think I actually, but I could put the microphone up to this thing, and I could talk into it, and you'd see that it would actually give you that kind of thing. Any questions? Yes, no. Now, we call this amplifier, this is called a common emitter amplifier, because the emitter is common to both the inputs and the outputs. So notice the emitter is common to not only the input, it's also common to the output. Now, what AC sees, let me find me a blank slide. I'm going the wrong way. I know y'all need to take a break. So this is what your AC sees. Your input sees. I've got a capacitor right here. That's what it sees. Because AC sees your DC source as a straight DC block. Okay. Now your output sees this. RC in parallel with the load. So your output is generated at the collector. So your output is relative to the collector, right? You understand? So your input sees R1 in parallel with R2. It actually sees, but this guy here is going to be RE times beta. So normally we ignore RE. So I'm up here, I've got a 10K resistor. This is a 100K resistor. So what would my output be? What would the R of my output be? It's going to equal to RC in parallel with RL. So what would that give me? Huh? Huh? Well, yes, but we're trying to figure out why I'm not getting a gain of 10, so we're not going to ignore it now, so that's a good point. What does it come up to be? 99? So my gain would be 9.9 divided by 10. So it's going to give us a gain of what? Oh, this is K. This K's up. Should give us a gain of 9.9. So one volt peak to peak in means I should get 9.9 volts peak to peak out, and that's not. Oh,
Well, then I think about
on campus.
right now, I'm thinking of lab 32. What lab do you be caught up to?
Well, we'll probably have to do the transistor lab online.
So we need to, this lab is lab
33, 32, I think. They have two. I think 31 is the first one.
32 is rectifier 30.
Okay, then I'm wrong. 30, thinking about a different lab.
We need 33 data after that.
No, it's cloud.
November will be gone before we know it.
We might know who the president is. That's it. We do know the president is, but it might be the official. I don't think it is. I don't think Trump will ever give up. It wouldn't surprise me if the sheriff didn't have to come in and remove him from the White House. So this is a program we used to have called Electronic Workbench, which is really neat. It allowed us to simulate circuits. But unfortunately, when they came out with Windows 7, they dropped off support for 16-bit applications. So I don't know, that was a big thing. So I've still got Windows XP running on one of my computers at home because I have some games that I used to play all the time. Of course, I don't have time to do that anymore. So what I'm doing when I measure my output voltage, so 100K, we still should expect to gain pretty close to 10. But when I come up here and measure it, let me bring my camera back up. So the yellow is my input, it's on the top. And then my blue is my output, it's on the bottom. I'm taking it on the other side of the capacitor. So I'm taking it on the AC side. So I have 50 millivolts per division, so that would be 150 millivolts. Are you okay there? So 150 millivolts in, I've got my channel 2, I've got it on 500 millivolts per division. So that would be 1 volt. And that would be 500 millivolts, that means 10 millivolts per minor division. So that's what's nice about that. So let me move it over and fit it on that. Yeah, that's 10, that's 30. So that's 1.3 volts. I'm sorry. Yeah, 1.3 volts per division. So that would be a gain of what? So I had a gain of 10. When I bring 150 millivolts in, I should get 1.5 volts out. But here I'm getting 1.3 volts out. So that's 1.3 divided by 150 millivolts. That's still pretty good. That's still pretty close to what we calculated, right? You understand? What's that? 8.6. So, but I can change the frequency as long as I keep it within the bandwidth. I can change the frequency, notice the gain. I can change the input voltage, which is what audio would be doing. And notice the gain stays the same. Except I'll come over here, I'm going to keep going up, I'm going to keep bringing my input up. You see what's happening? Let me move my blue. I'm gonna get rid of my. I'm gonna move my. I'll move this up so you can see what's happening to my output. So here we got no distortion. Here we got no distortion. And then you notice when I get to a certain point, the bottom starts flipping. You know, see that? Well, what's happening? Well, I'm subtracting out where I don't have 0.7 volts anymore on the base, and the transistor cuts off. And I can't get it. You can see the top. You can see the top start flipping a little bit. So when you bias this thing, what you're trying to do is you're trying to put your collector, your VC, you're trying to put it exactly in the center. Now, what's the odds of that? so if this is 20 volts, what's the odds of me getting that right there exactly at 10 volts? Well, when I could calculate it, I wrote a program one time that would calculate all these resistors to set it in the middle. But the problem is your calculated values, odds are there's probably 100% chance there's not going to be a standard resistor that fits that calculated value, right? You understand that? So what you got to do is you got to get it as close as you can with standard resistors. Because standard resistors cost you what? Yeah, so we'll look at those. Yeah, those are the standard resistors. You know, so if I was to come up here and look at a place, these guys, you know, you can get like, I mean, these guys are almost nothing. Especially quarter watts. Quarter watts are a lot less than, so we use a parts place called Jamico Electronics. We order a bunch of stuff from these. So we'll just look up resistors. For some reason it's not working. Oh, I know it's good. Got it. On this one, you got to hit search. So this guy right here, this is a quarter watt resistor. I can get 10 for 6 cents. But these are all going to be what? If I order them in groups of 1,000, then they're less than 1 cent a piece. So these guys are mass produced, right? You understand? So these are standard resistors. I could use a rheostat. So here, it's going to cost me 6 cents, or it's going to cost me $5 for a rheostat. Well, you can't hardly get rheostats anymore because potentiometers can serve as a rheostat. So I pay $5 for a rheostat, or I pay 6 cents for a resistor, right? You understand? Well, it's actually not 6 cents because that's for what? That's for 10. So that's 0.06 cents, or less than a penny a piece, these things cost, because they're mass produced. And if we went to eighth of a watt, we'll see that those guys are actually more. So why would an eighth of a watt be more expensive than a half watt? They're not as big as demand. So here's, oh no, that's resistor pack. I don't see that. So quarter watt, so the only thing I would use an eighth of a watt resistor for is if I was limited for size, the space that I would, if it meant going from a printed circuit board this big to a printed circuit board that big, then I'll use an eighth of a watt because I would save money on the board itself, right? You understand that? So engineers are going to use whatever's cheapest for them to do. So let's see what, okay. So one more thing. And we got one more amplifier we need to go through. There's actually 3. We have what we call a common emitter. You'll see why it's called a common emitter? Because it's common to both the input and the output, right? You understand that? Remember, the input sees that VCC as 0 volts. It sees it as a common. But we're limited to the gain. So the gain is set right now is set by this resistor in parallel with your load and this resistor right here. So we're not going to get, and what we're trying to do is we're trying to get impedance matching. So I would not take, this amplifier has a pretty good input impedance, right? You understand that? It's going to be around 10K. And y'all can calculate that, guys. Oh, no. But we're not going to do that in this class. What did I do with my PowerPoint? So the input impedance would be this guy, and then it's going to be this and parallel that with that times theta. So normally it's just going to be these two guys right here in parallel. So ours would have an input impedance of around 9K. 9.9K. So I would want, if I was going to try to get impedance matching, that means whatever's feeding this guy would need to have an impedance of around 9.9K. But the problem is that it's so hard to do that because we're dealing with standard resistance. So basically we say, okay, if a transistor's got a high input impedance, I want to match it to something else that's got a high output impedance. And if we got a low output impedance, that works. So to get maximum power transfer to all these amplifiers is very, very hard because of not only dealing with standard resistors, it's also dealing with trying to match impedances between input and output. So design of these guys is not easy, guys. But we're not trying to teach design. We're trying to teach you, okay, if I come up here and I measure my base voltage, and if it's not what it's supposed to be, what could cause that? What could that cause that? So if I came over here and I measured, if I knew I had 20 volts right there and I measured 0 volts right there, what could be the problem? Well, the transistor would be cut off, number one, because the base voltage is 0. But what would be the first place I would look at? R1. You're exactly right. Because that's what gives, this and this are what's setting that voltage. So if this measures 0 volts, then the first place I would look at R1. That's the first place I would. What if it measures higher than what it's supposed to be? Huh?
Higher. I would still look at R1.
Well, if R2 opens, then that base voltage is set at this times base. So now my voltage divider looks like this. Now I cannot ignore this resistance. So this guy right here is real big, right? It's seen as times beta. That'll call that base voltage to go up a lot. So if my base voltage was way too high, I would assume that R2 did. What if this guy right here was okay? This guy right here was okay. I come up here and I measure 20 volts right there. What would be the problem? What's that? RC. Right? What if this right here measured extremely low? It measures 0, but measures extremely low. Well, if the capacitor's short, it would measure 0. So that happens too. Capacitors can short, guys. So if I measure 0 volts there, or extremely low, then it could be the capacitor. It could be the capacitor leaking. But what would cause this to go real low? Another thing would be if I lost IC. If for some reason I lose IC, then we lose beta. And this resistor over here is no longer seen as times beta. So it'd be a 1K in parallel with 10K. So now the 1K is setting the beta. So what we're saying, if you understand this bias, and we can measure this bias even if the circuit is active. Because even if it's audio, it's still going to be an AC signal, right? You understand that? So does everybody understand this? So if I went to each one of y'all and I asked y'all a question, why can we ignore RE or anything like that? Or if I asked you if you could calculate these base voltages, would you be doing that? Or you would be sitting back here twiddling your thumbs or doing like this? I don't know, guys. Sometimes I don't understand why you're paying the money to come here to sit back there and tweak on your telephone and all that other kind of garbage. You're not paying any attention. Or I don't know why you're doing that, because I test on this. Right now, some of y'all, and by the way, guys, these labs are not a group effort. These are not a group effort. So I've got problems with this class of people copying their labs, and that's not going to work in this class. That is not going to work, because if you copy, the only thing you prove to me is that you can do what? Copy. Right? Y'all understand that? And then now, from now on, when you take my class, I'm going to look at you extra hard, right? I'm going to look at your papers extra hard because you cheated in my classes before. And not only that, I'm going to tell the other instructors that I'm over that you cheated in my class. So now you've got to represent. We had for some reason, automotive decided they wanted our students, they wanted their automotive students to take video and take an electronic course. And those guys, what they take, they say, that's a good one. So I got a video for I didn't turn it on. But this time of class, a lot of people don't know stuff like in class. You know, they does what? The cheese are way. And the problem is, our reputation, how long does it take?
I never really watched my, but,
Something like this, you say, I don't know. I don't. It's also, so I had a product, like, go buy something. Buy a product one, and I'm already going to go up. You're not going to buy it. So, you know, when I look at questions, and there's questions on a lab, and they're exactly the same. When I look at voltage measurements, and they're exactly the same. And what's the odds of that being? So, guys, like I said, I know some of y'all are redoing some labs that y'all had to, you know, for that reason. And I appreciate y'all doing that, but what I'm trying to do is I'm trying to get y'all to put a good product. Are you going to have to ever calculate these voltages when you get out in the field? Probably not, because normally schematics, they do that for you. Right? But now you understand why it's there, right? You understand, and this is what I'm, and of course, why we do a lot of computations in these classes, and like I said, that concerns me, where you calculate one thing and you measure another one, and then you do what? You move on, right? Like in DC, you know, you got a series circuit, and you measure 0 volts, and you write 0 volts down, and you know it can't be 0 if it's a series circuit, right? You understand that? So that's the kind of stuff that we're trying to teach you. So no, if there's one of these on the test, so this will be a bonus. Now we're going to give a worksheet out, right? Worksheets, of course, worksheets are graded according to what? Effort, yeah. So we got one more thing to look at this. So if I overdrive my circuit, it's going to give out a distortion because my input signal is either going to be high enough to saturate it or it's going to be low enough to cut it off, right? So I think I told y'all, since the output is 180 degrees out of phase, this would be, if it clips up here, it means it's saturated. If it clips down here, it means it's cut off. So what I'm doing is my input is big enough. I'm sorry, up here it's cut off, down here it's saturated. Did I say that right? So here on the output voltage, it's opposite of the input. So if it drops 20 volts, that means it's cut off. If it drops 0 volts, that means it's saturated. So what that means is this means I'm inputting this thing enough to saturate. If it's cut on here, if it's clipped on the top, that means it's what? It's cutting off, right? Y'all understand why? Because I'm taking the output across the transistor. And it's 180 degrees out of phase. But I can, as long as I stay within these boundaries, and you can hear people that's got poorly designed stereos. I've heard stereos, it's all the story. One thing, they might be overdriving it. So what's happening is they're putting an input signal into it, and they don't have enough voltage to work with, right? Another thing is they don't do impedance matching. So a lot of people think you get those stereos, you want to add multiple speakers, you just hook them in parallel. Well, they're 2 ohm speakers. So if you hook 2 in parallel, you drop down to what? 1 ohm. If you hook 3 in parallel, now you're getting out of impedance matching and you get distortion anyway. So what do? You hook some of your speakers in what? Parallel, and you hook some of them in what? Series, to get the maximum power transfer. So people don't understand that. So now you know why stereos give you awful sound, right? Either they're doing what? They're not hooking their speakers up right, or they're hooking them out of phase. By the way, speakers are phase. Why do speakers have plus and minus on them when we put AC on them? Why speaker wires, one of them, they're either red and black, or one of them got a little groove on it? Why is that true? Well, if you hook them up out of phase, then when this speaker's going out, this speaker right here is going in, right? You understand? So that's why you got the polarity on the speakers. That's why you got, because it tells you to take the same wire that you hook up on one and hook it to the other. So you're putting AC on those speakers. So now you know that. So you can't hook up those wires any way you want to. If you hook up one backwards, then what's happening? When this one's going out, the other one's doing what? Going in, and you're not getting the sound you want. So you can hook them in parallel, you can hook them up in series to try to maintain pretty close to 2 ohms on your stereo, right? So most of them got a little range on that. House speakers are 8 ohm speakers. So if you take a house speaker and put it on your car radio, you're going to get crummy sound too. Why? Because you screwed up your impedance matches, right? So now you understand that kind of stuff. So you just can't, if you have a coax wire break, you just can't strip them and twist them back together. If you get one of these network cables up here that breaks, you just can't twist them back together, right? When you crimp those things, if you ever made network cables before, when you crimp them, you got to maintain that twist as far as you possibly can. You just can't twist wires together, because now you understand why, because you screw up your impedance matching. So we have cables, so you cannot use just a piece of wire to run a network cable. You can't just use pieces of wire to run your antenna, right? So because of this impedance matching. So now we understand that. So now you're okay. You understand distortion. You understand impedance matching. So even though you can't calculate these, you understand a lot of things that could cause what? Could cause problems in the system. So one more thing. What I'm going to do is I'm going to take this circuit right here, and I'm going to do something very interesting. Is I'm going to come over here, and I'm going to take a capacitor, and I'm going to take a capacitor, and I'm going to put it right here. What I just did is I lowered my input impedance a lot, but we're going to get a ton of gain out of this. A ton of gain. So what my AC signal is doing now, so used to my AC signal was coming in and doing this. This is the original path for my AC coming in. It's coming up here. It's going this way. Because AC sees this, right? You understand? AC sees that. It's coming over going this way. coming over here, going through here. Why don't the AC go that way? It's reverse bias, right? It's reverse bias. Okay. Alright. So what would happen if I came over here and put a capacitor right there? Well, now, as long as I'm in the range, my AC signal is going to do this. There comes my AC signal. Still going this way, right? Still going this way. Now, my 1.1 volt is DC. So that 1 volt is still there. That's DC. But what my AC signal is going to do is it's going to bypass RE. So this is called a bypass capacitor. These are called coupling capacitors. So now my gain is no longer RC over RE. So what is my gain? Well, you're going to say, I don't know. So what we have to do is we have to deal with, we know that that guy right here, so when we come over here and forward bias at junction, it actually comes over here and does this. Everybody okay? So what we do is we deal with what we call the dynamic resistance of a P junction. This is when we put AC on. So I meant to give this out to you. So calculating the dynamic resistance of a P junction. They're coming to a minute, guys. Hopefully. So this is the formula for calculating the dynamic resistance of a P junction. So we deal with the derivatives, a little calculus. And then they finally come up with this formula right here. So what does it say? Down near the front. That's probably your reference statement. Of course, this is not a 25 millivolts. It's probably on your formula sheet. So we call this RE prime. That's what the little thing up there. So that way we have a difference between RE and RE prime. So when I put that bypass capacitor, this is what my RE becomes. It becomes 25 millivolts over RE. I'm sorry, IE. So what would that give us? So what did we come up with? So we had 1.1 volts, so we got 1.1 milliamp. Ohms. So we take 20 what? 23 ohms. So my gain, if we bypass that thing, my gain goes to right now, let's just use 10K. 10K over 23 ohms. So 435? Okay. So, watch this. I'm going to bring my camera back over here. Now I'm going to have to lower my input voltage down to basically something that's going to be so small that we're going to pick up a lot of noise. But the noise is not there right now. And I'm going to take my input and I'm going to bypass my emitter resistor. So here's my emitter resistor. I'm going to put my negative toward the common. Then I'm going to put this over here. Touching guys. Notice my signal came so distorted. So here's my input up here. So I'm going to turn it down and see what we got. Let's switch it over to trigger channel 2. So now I've got my input is, I have on 5 millivolts per division, 5, 10, 15, 21, 22, 23, 24, 24 millivolts in. 24 volts. I got it on 5, my output's on 2 volts per division. So I got 4.8 volts out. So 23 millivolts in, 4.8 volts out. So what's our gain? Yeah. 208. Now this our gain is really off. But I'm getting a gain of 208. I've got my input turned down so low it's actually picking up noise. So you can see we're going to come up here and We're gonna overdrive this one really easy. So the gain is so high. So here we're okay. Here we're starting to saturate. And of course here we're cutting off. So if I bypass it, we get extremely high gains, but we sacrifice it by input impedance. So the input impedance drops way down. If we don't bypass it, we get a higher input impedance, but we can't get real high gains. That make sense? Y'all see the circuit? So I have several methods. We've got different ways. We have what we call a swamp arrangement, but we're not going to get into that. So these two capacitors right here are called what capacitors? What's the name of these capacitors? Yeah, they have a name. Starts with a C. Yeah, these are coupling capacitors. And then if we put one down here, it's called a what? It's called a bypass.
Over the ones in line.
These are called coupling capacitors. So that's what they do. They allow us to couple an AC signal in and get an AC signal out, right? Understand? Now we might come up here to do this, guys. So I might come over here and I might bring this into another amplifier. Oops, sorry. Now, what engineers are doing, so to set the gain on this one, we would have to calculate the input impedance of this guy in parallel with that. So this really gets complicated. But what we do is we start off with something, we want something, we might start off with a low gain, right? You understand that? Because we're trying to bring a high input impedance sensor into my amplifier. And then after that, we will, once we get enough voltage, then we want to keep getting higher and higher gains, right? You understand? This guy right here, it's going to give us, so characteristics, the input and the output are always going to be 180 degrees out of phase. Rich, out of phase, right? Y'all understand that? We can get a voltage gain out of this. If we get a voltage gain, what other type of gain can we get? We could get a current gain depending on how it's. And if we get a current gain and a voltage gain, of course, we're going to get a power gain out of it. So that's one of the characteristics of a common emitter amplifier. It's got a high output impedance. Depends on whether we bypass or not, according to the input impedance. Y'all know what input, we talked about impedance, right? What's impedance? It is an opposition, but what has happened over time, because it really sounds cool, right? Impedance, I think most people don't have a thought that we're talking about, so we like using words that other people don't know. But technically, it's a opposition to an AC signal in a circuit that has both reactive and resistive devices. So what you'll find out is a lot of people in AC, they talk about the opposition of impedance anyway. They don't use a resistance at all. And when we try to get maximum transfer between systems, we're trying to do what? We're trying to match the impedance between them as soon as possible. So if I'm coming over here from a sensor, like a microphone, so I don't know what the impedance of this. Can I measure the impedance of this with an ohmmeter? Huh? But it's an inductor. Because it's a bunch of coils of wire. Just because it's in ohms, it don't mean it's a meter. Your meter measures resistance. Your meter does not measure impedance. Your meter measures resistance. So what's the difference between resistance and impedance? They're both measured in ohms. It's ohms is opposite. Yeah, you know, also an ohm. So if I measure across the table, you know that transformer silver take both of them. Opposition that's set on this formula right here. So X of L, so as soon as I put 60 cycles on that transformer, that 2 ohms is out of whack. And we can use it to check the traffic. So if I got a transformer, so if I'm going to measure X of L, I've got to have something that takes into consideration what? Frequency, which is very hard. So we calculate X of L, right? You'll learn that in AC. So when we talk about impedance, normally we're talking about AC. So the input impedance of this amplifier would not only be set right there. So if I put 1 hertz on this thing, then my input impedance is going to be real high. Right? If I put 1,000 hertz on this, the input impedance is going to be real low because on the capacitor part, 1/2000 LC. So inductors, if the frequency goes up, so this is why your transformer is going to turn up. If you put DC on the transformer, it's going to go up. If you put DC on the power figure, it's going to turn up. So that's what happens sometimes. Your output's short and you're protective on your big amplifier on the shelf. And you come over there and keep resetting for the speaker. Now you're not dealing with the veil. So the X of L of the speaker is usually set at about 1,000 hertz. So if I put my ohmmeter across the speaker, if it's an 8 ohm speaker, what should I expect it to measure? More than 8 ohms or less than 8? Huh? Less, because we're taking away the what? We're taking away the L. Now we're only dealing with the R of okay. Well, the 8 ohms is said that the 8 ohms is said that X of L is equal to what? 1,000, 8 ohms at 2, at what? 55 problem is, to measure it on, you gotta have an F component. But an inductor is nothing but a bunch of full wire. So you can measure an R of an inductor, but that's not going to be the watt. That's not going to be the impedance of the signal. So what you're talking about, if I come over here and measure this, if I measure a big bass speaker, odds are it's going to have a lower resistance than like a quitter speaker, right? Because it's got a lot more current wire, right? Does that make sense? And a bass speaker has zero current. But now we understand that. So I understand that they call it the 8 ohm speaker. I understand if I measure the 8 ohm, I'm not going to measure what? It's not going to measure 8 ohm. I don't think I'll do it. So this guy measures well, I don't know, this guy right here measures something. So this guy right here measures 42 ohms. So you would use this on your house stereo, right? And if I put 1,000 cycles on it, and then measure, so you got a capacity, so this meter right here got a capacity check. So how does this thing check capacity? How does this thing check capacity? No, but it actually measures the capacity. It's got but it's got an M component, so it actually puts out it actually has an oscillator in there that puts out a signal, right? And then it uses this calculator. So this guy measures the capacity. But the only way you're going to measure the capacity is if you don't have a capacity meter, then you know how to make an oscillator. We don't get time to make oscillators. You can set up a little oscillator circuit. You can measure the inductive capacity. So the problem we have with this, of course, is first of all trying to measure this input resistance. So if I turned all the power off and I tried to measure this, it's not going to measure right? You understand that? So first of all, the AC signal is not there anymore, so it won't see this as 0 volts. So we cannot measure the input impedance of an amplifier. We can calculate it, but we can't do what? We can't measure it. So I come up here and I measure that resistor. I can measure across the resistor, but I can't say, okay, that's going to be the impedance of the amplifier, right? So we calculate. And I showed y'all a little bit of math, and that's okay. We're not going to do that in this class. But what we'll do is we'll understand. What we're going to do is figure out what these voltages are when things are bad. So let's calculate this and see if this is what. So this is what they. So this is the math, and this is with an AC signal or without an AC signal, right? Y'all understand that? Yes or no? So I come over here now and I make these measurements right here. So every one of these is cut off. So notice VC is setting at 10 volts. So the transistor is cut off for some reason. So the first one says VE is equal to 0 and VB is equal to 0. What's the problem? What do you think, Cameron? What do you think, Blake? What do you think, Grant? Who agrees with R1? No. Huh? Well, no, we got 0 votes right here. Now, if we had an input capacitor, the input capacitor could be shorted, but we're not looking at that. Most of the things we can get it down to two parts. So what sets this voltage right here is this voltage divider. If I've got 0 volts right there, that means this 10 volts is not, right? So that means this guy right here would be what? Open. So here we measure 10 volts. Here my VE measures 2.5 volts. And my VB measures 3.2 volts. What's it supposed to measure? Let's record those over. So BR2 is 3.2 volts. BE should be 2.5 volts. We're not going to measure IE. We're measuring bias. VC should be 4.7 volts. So these are the ones we're interested in. This one, and this one. Those 3 measurements right there, basically, with those 3 measurements right there, you can tell what's wrong with the current. Somebody write that down. So VB is 3.2, VE is 2.5, and then VC should be 4.7.